the ideal gas law. We can take all of these laws and combine them into one. The other way to think of it is you can make all the other laws out of this one law. It's called the ideal gas law, and it's PV equals nRT. And really, this is the only one that you need to memorize. PV equals nRT, and I will show you how you can make the other ones just by using PV equals nRT. So we have a new letter in here, capital R. Capital R is the ideal gas constant. In a proportionality, you have things, well, this gets bigger, that gets smaller, etc. But if you want to make an equality out of a proportionality, you need a constant. And so here's the constant. It's 0.0821 liters times atmospheres divided by moles times Kelvin. And yes, those units are awkward, but these are the units that P, V, N, and T are in. And so we use pressure in atmospheres. When we're using this gas constant, we have to put the pressure in atmospheres. The volume must be in liters. The amount of gas, N, must be in moles. The temperature must be in what? Kelvins, right? So this number, which I will give you on an exam, although I think you'd save a lot of time by memorizing it, the units tell us what units we need to use on the other quantities in this equation. PV equals nRT. Sometimes people call it PivNert. Trying to throw a couple vowels in there to pronounce it, PivNert. This is a table that shows you the relationships between the ideal gas law and what are called the simple gas laws. So I'm going to show you a little trick here. So PV equals nRT. That's an equation, and if I divide both sides of the equation by the same thing, it's still equal, right? So if this was P1, V1, N1, and T1, if I divided by P2 times V2 on both sides, would that still be equal? Did I do the same thing to both sides? I did. So this is still equal to that. What does P2, V2 equal, though? It equals N2RT2, right? Do it this way. So that's equal to N2RT2. I'm not giving R a subscript because R is a constant, it doesn't change. So what I did is I took the ideal gas law, PV equals nRT, I gave it subscripts of 1. I divided by the ideal gas law with subscripts of 2. If you have more questions about how you can do that mathematically, I'd be happy to talk to you about it. Now we can cancel out anything that doesn't change. R doesn't change. So R over R is 1. It cancels out. Let's think about, pick a gas law. Boyle's, Charles, or Avogadro's. Somebody just say one. Boyle's, thank you. So Boyle's law relates pressure and volume. The pressure and volume change, but the temperature and the amount of gas do not change. So for Boyle's experiments, T1 was equal to T2, and N1 was equal to N2. He didn't allow the temperature to change, and he didn't change the amount of gas. So if N1 equals N2, then N1 over N2 is 1. They cancel out. If T1 equals T2, then T1 over T2 cancels out. And what do we have left? I'm going to move to the bottom. We have P1 V1 over P2 V2 equals what? What does that equal? What are all these canceled out things equal to? 1. What if I cross multiply this? Don't be bothered by the fact that there's no fraction over there. It could be 1 over 1. What do I get? P1V1 equals P2V2. And that's Boyle's law. You can do that for any of these gas laws. Here's one we didn't talk about specifically. Gay-Lussac's law relates pressure and temperature. And the combined gas law just has changing quantities of pressure, volume, and temperature. So that can save you a lot of memorization. PV equals nRT with subscripts of 1 divided by PV equals nRT with subscripts of 2. Look at your problem. Anything that's not changing, cross them out. Take what's left, rearrange it for the variable that you're solving for. Okay, let's do a straight ideal gas law problem. Calculate the volume occupied by 0.845 moles of nitrogen gas at a pressure of 1.37 atmospheres and a temperature of 315 Kelvin. So here we've got numbers. There's 1, and there's 1, and here's 1 over here. Let's make a table, because that's what we're learning to do. Make a table. So the first number, 0.845 moles. In the gas laws, what variable is moles? N. N for number of moles. Here's condition 1 and condition 2. So that many moles at a pressure of 1.37 atmospheres. 1.37 atmospheres. That's pressure. And a temperature of 315 Kelvin. Ooh, they were kind. They gave us the temperature in kelvins. I don't have any numbers for down here. Is that a problem? No. So I made a table and there's no second row. What do I do? Well, I'm just going to erase the second row because it turns out I didn't need that. On an exam, it can be a little challenging for a lot of students to just read the problem and know which gas law they need to use. The table always works. Make the table. It will give you a big clue what to do. Here, this one is showing us I have N, P, and T, and nothing is changing. There's no 1 and 2. I don't have multiple pressures or temperatures. That tells me I need to use PivNert. So PV equals nRT is the equation I'm going to use. What am I trying to find? Volume. So in PivNert, I'm trying to solve for V. I'm going to rearrange the equation first. Divide by P. P cancels out. I have to do the same thing to both sides. So volume is nRT over P. N is 0.845 moles. Probably a good idea over here to write down what R is. R is 0.0821 liters times atmospheres divided by moles times Kelvin. Check your units. Make sure that the units you have here match up with these units. If this pressure, if the pressure was in millimeters of mercury, I need to change it to atmospheres before I put it into the equation. This is a nice, easy starting problem, and so we don't have to mess with any of the units, but it will happen on homework. So then I've got R in here, 0.0821. I know it's a pain to write those units, do it anyway. Because taking the class over again is a pain as well. 315 Kelvin. And pressure down here, 1.37 atmospheres. So Moles are canceling, kelvins are canceling, atmospheres are canceling. This is good. I'm ending up with liters as the remaining unit. So 0.845 times 0.0821 times 315 divided by 1.37 equals. How many significant figures should this have? It should have 3. So it's going to be, it says 15.95107, etc. So I'm keeping this one. That's going to round up to 16.0 liters. Any questions? Did you ever wonder how they determine the molar mass of a compound? Because, the molar mass is grams per mole, and mole is Avogadro's number of things. So, you think somebody sits and counts out 6.022 times 10 to the 23rd molecules and then weighs them on a balance? That's not going to work, is it? One way that you can find a molar mass for a volatile compound, meaning it evaporates, it goes into the gas state easily, is by turning it into a gas. We can figure out the moles of a gas using the ideal gas law. So here, a sample of a gas has a mass of 38.8 milligrams. Its volume is 224 milliliters at a temperature of 55 degrees Celsius and a pressure of 886 torr. Find the molar mass of the gas. We can do this. So molar mass is mass per mole. So we need the mass of the gas, and we need to know how many moles are there. They gave us the mass, didn't they? Although they gave it to us in milligrams. So that's 38.8 milligrams. Molar masses are generally grams per mole. So we need to convert that to grams, multiply by grams, divide by milligrams. What does milli mean? Thousandths, yes. 1 times 10 to the minus third. And then the milligrams cancel out. So we end up with 0.0388 grams. So that's the mass of the gas in grams, 0.0388 grams. How do we find the number of moles? We have a temperature, we have a pressure, we have a volume. $224, oh, that's not where I meant to write that. 224 milliliters is the volume. 55 degrees Celsius, what do we need to do to that? Put it in Kelvin. .328 Kelvin. That's the temperature. And the pressure is 886 torr. So we're going to use PV equals nRT. What are we solving for this time? Moles, N. Solving for N. So if I want to get N by itself, I need to divide by the other guys that are with it, R and T. I need them to go away. So these guys cancel out. If I do it to that side, I have to do it to this side. So N equals PV over RT. Are these good units? Where's my pointer? There it is. Are these good units? The kelvins are good, but the torr and the milliliters are not. Because the ideal gas constant, 0.0821 liters times atmospheres per moles times Kelvin. So I need this volume in liters. So 224 milliliters. Milliliters on the bottom, liters on the top. Milli means 10 to the minus third. Gets me 0.224 liters. And torr to atmospheres, 886 torr times 1 atmosphere per 760 torr. We just learned how to do that today. 886 divided by 760. That will be 1.1658. 3 sig figs. I'm just carrying a couple extras. Atmospheres. No, that's off the screen. Atmospheres. So I'm going to take my volume and my pressure, and I'm going to convert them so that all of my units match up with the ideal gas law, constant. So pressure, 1.16, I can't read what I wrote, 58 atmospheres. And the volume, volume, 0.224 liters. Divided by R, 0.0821 liters, atmospheres per mole Kelvin, times the temperature, 328. Now be careful, we got 2 numbers in the denominator. So I've got 1.1658 times 0.224 divided by 0.0821 divided by 328. Or use parentheses if you have to. 0.009697. How many sig figs should that have? It should have 3. So I'm going to underline the third one. And I'm going to bring that guy up here. 0.009697 moles. That's got 3 sig figs. The number on top has 3 sig figs. 0.0388 divided by 0.009697. And this equals 4.00 grams per mole. Anybody know what gas that is? It's helium, yeah. Helium is the second smallest element. A smaller element is hydrogen. We know that hydrogen is a diatomic molecule, and it's got a molar mass of 1. The diatomic would have a molar mass of 2. So this is too high to be hydrogen, and nothing else is small enough to be the same as helium. So this is helium. But that's how you can measure the molar mass of a gas. Any questions? So this is combining 2 ideas, right? Molar mass, what is it? It's the mass of something divided by the number of moles of particles in that mass. And we're using the ideal gas law to find the number of moles of the gas. We've seen through these gas laws that gas behavior depends on conditions. And we said at the beginning that the kinetic molecular theory describes the behavior of gases under most conditions, but that there are some conditions under which it doesn't work. What we call ideal gas conditions would be relatively high temperature and low pressure. In these situations, there's plenty of space between the particles, and they're moving fairly rapidly. And so the interactions between particles when they bump into each other is insignificant. And the size of the particles is insignificant. When things get crowded, the situation is different. So a non-ideal condition is low temperature and high pressure. With high pressure, these particles now are starting to take up more volume because they're squished closer together. There's less empty space. And so the size of the particle begins to matter. And the slow speeds result in when these particles run into each other, they bump in slowly and they're spending more time close together, and there actually is an attraction between the particles. And so it starts to become significant at very low temperatures. So under these sorts of conditions, the gases do not obey the laws.